Hi everyone and welcome back to my channel. So today we will start with the lecture 5A of cache memory. So in today's lecture actually we will discuss about block replacement techniques. So when do we need to replace blocks? When there is a miss. So when there is a miss, we replace the blocks. So let's say my cache memory currently has 4 blocks in it, right? It's like a direct map. It has 4 blocks, block 0, 1, 2, 3. All of the blocks are full and main memory is here. So let's say there is a cache miss. So if there is a cache miss, that means what? That means that block is not present in the cache memory. I have to go into the main memory and bring that block into the cache memory. So when I will bring that block into the cache memory, which block will I replace? Will I replace the block 0? But you also know that in direct mapping there is no option, right? Every block has a fixed block number in the cache memory. You will replace that block only. But in two-way set, if it is a two-way set, right? If it is direct mapping, there is no other option. Of course, like whatever, let's say this is, I have 8 blocks here, right? So the block 0 will go to block 0. Again, the block 4 will go to block 0 only. Correct? There is no other option, right? I have to replace the block 0 only. There is no other option in direct map. But in the two-way set, if it is a two-way set, that means what? That means let's assume that here my cache memory has two sets and each set has two blocks. So this block 0 of main memory, can come here or here, and assume that both of them are full initially. So which one will I replace? Will I replace this one or this one? Which one shall I replace? Because of course I know the block number of 0 should come in the set number of 0 only. That much I know. But here I have two blocks. Which blocks shall I replace? I don't know, right? Which blocks shall I replace? So I have to decide. I have to put a ranking system. I have to prioritize something. Then only I can replace. Okay. So yeah, I hope you have understood this basic point, that for this we need few block replacement techniques that I will understand, and after that of course we will understand about type of cache miss. What are the different types of cache miss? Okay, there can be many types of cache miss, so we will see that. So first one is like first of all your, okay, where is the direct, okay, direct mapping should come first actually, I guess. Yes, direct mapping. Okay, it has some problem with the this. So for direct mapping, in case of direct mapping, you don't need any block replacement techniques. So in direct mapping, what happens? Here I will say no block replacement technique is required. Why no block replacement technique is required? No block replacement is required. Okay, no block replacement technique is required. Right? Because let's say my main memory has 16 blocks, my cache memory has 8 blocks. What is the mapping formula? Very simple, right? Just main memory block number mod number of cache blocks. So if let's say CPU requests for main memory block 3, then where I will go? In the cache memory, where I will go? In the cache memory, I have 8 blocks, right? So it is 1, 2, 1, 2, 3, 4. Then again, I have 8 blocks. 1, 2, 3, 4. Okay. So yeah, I'm sorry for that noise. So this is my cache memory, and main memory has some blocks. Okay, 16 blocks it has. So if I am requesting for block 3 from the main memory, where it will stay in the cache memory, it is 3 mod 8, that is in the block 3 only. So it will be 0, 1, 2, 3 here. Okay, and let's assume initially it is not present. Initially block number 11 is present. So if initially block number 11 is present, then I had to go to the cache main memory and bring the block number 3 here. So do I have any other option than replacing this 11? Do I have any other option than replacing this 11? Can I place this 3 anywhere else? No. This 3 can be placed only in one single place, that is block number 3 of cache memory, and there is only a one storage space of block in a cache memory, right? Only I can store in a single block, or in a single block number I can only store one block, correct? So I have no other choice than to replace this 11. So that's why there is no block replacement technique required. So once I will come to the next one, we will understand how block replacement technique will be required. Okay, so that's how, like, simple cache memory block of 3 will be also mapped to 3, cache memory block of 11 also will be mapped to 3 only. Okay, it will be mapped to 3, not it will be mapped to 3, cache block of 3 only. So this will be 3. Okay, now let's understand set associative mapping. What happens in set associative mapping? In set associative mapping, the cache is divided into sets and each set can hold multiple blocks. Okay, the cache is divided into sets and each set can hold multiple blocks. That means each set has multiple blocks in it. So let's take example that my memory has 32 blocks. Okay, my cache has 4 sets. Actually it has 4 sets, 4 blocks grouped into 4 sets. So my cache memory has 4 sets. Okay, it has 4 sets. So yeah, now set 1 is here, set 1, set 0, sorry, set 0, set 1, set 2, set 3. Okay, so each set has 4 blocks. Each set has 4 blocks. Each set has 4 blocks. So this has 4 blocks. So this will be the like each set has 4 blocks. So in this 4, right, anything can stay. So in state set 0, what numbers can be there? What block numbers can be there of main memory? 0, 4, 8, 12 and so on. Okay, and in set 1, what block numbers can be there of cache main memory? 1, 5, 1, 5, 9 and so on. And in set 2, what block numbers can be there? It will be 2, 6, 10 and so on. And in set 3, what block numbers will be there? 3, 7, 11 and so on. Okay, and so on. So these will stay there, right? So if now let's say initially I have here I am requesting for block 1. Okay, initially I am requesting for block 1. So let's say I have here the blocks as 5, 9, 13 and 17. So these are the main memory blocks present. Now the CPU request for block 1. So CPU comes here, CPU comes, this is a 4-way, right? No, 4-way. So CPU comes here and ask, like, as it is block 1, if it is block 1, I will do 1 mod of my set number, that is 4, it will come as 1 only. So I will go into the set 1 and I will check whether I will match the tags. I will match the tags. Are any of the tags matching? So I will see that no, none of the tags are matching. Basically none of the cache main memory block numbers are present here. So I will go into the cache main memory. I will go into the main memory and transfer the block 1 to my cache memory. I will go into the main memory and transfer the block 1 to my cache memory. Now as soon as I bring my block 1 to my cache memory, I have 4 options, because block 1 will be placed in set number 1. That is confirmed. I am sure about that. Block 1 will be placed in set number 1. But in which block of the set? Because there are 4 blocks, right? In a single set there can be 4 blocks. I will replace which one? Will I replace 5? Then 9 will say, why don't you replace me? Will I replace 9? Then 13 will say, why don't you replace me? So which one will I replace? For these kind of things, we have to have a policy. Okay, policy is required, right? What kind of replacement? We need a policy for the replacement. Whenever I am replacing, we need a policy. So we will understand those policies. So there are mainly 3 kinds of policies. So this one is first in, first out. So replace the block that has been in the cache for the longest. Basically, let's say initially everything was empty and I called 5, then I called 9, then I called 13, then I called 17. Now next I am calling 1. If I am calling 1, then which one will I replace? If I am following FIFO, whichever one I called the fastest, I mean first. So I called 5 the oldest, right? The oldest I called 5. So I will replace 5 now. Instead of 1, instead of 5 there will be 1. Okay. So yeah, this is what my first in first out it is. It is easy to implement, may replace frequently used block. So the problem is it does not take into account how frequently a block is getting used. It does not take into account that, right? Even though the block is getting used frequently, that whenever my cache memory is calling 5, we are, it is a cache hit, right? I'm calling it frequently, but as it was in the cache memory for the oldest period of time, it will get replaced even though we were frequently calling it. What do I mean? So let's take an example. Let's take a very good example, like same example here I have. Okay, so my CPU memory calls are somewhat like this. So initially my CPU initially cache memory is empty, so CPU initially called for 5, then CPU called for the block number 9, then CPU called for the block number 13, then CPU called for the block number 17. Okay, then again CPU called for the block number 5, again CPU called for the block number 5, and then again my CPU called for block number 1. Okay, so actually 5 was getting called multiple times here, but which one is the oldest that has been brought into the cache memory? The block number 5. So as soon as I call a new block, that is 1, the cache set is already fully filled, right? So I have to replace. Which one will I replace? I will replace the oldest one. So even though I see that I was actually calling my block number 5 twice before calling 1, but I had to replace it because I was following the first in first out. Okay, so that is the problem with first in first out. Advantage is easy to implement, but disadvantage is it may replace the frequently used block. So that is a disadvantage. So yeah, that is one of the disadvantage. Whichever, like basic thing is, whichever comes first will be replaced, will be replaced first. Okay, and also one more thing, basically who will like do this hardware, like who will do this replacement policies? A hardware present in the cache controller will implement this replacement policies in the cache controller. Will implement this replacement. Okay, next is the optimal replacement. What is optimal replacement? This is the replace the blocks that will not be used for longest time in the future. Like replace the blocks that will actually not be used. So we have to predict the future. So it's like a astro talk, right? Astro guy. So he is predicting the future. So we have to predict the future and tell that whichever blocks will not be used in a while in the future, those I will not replace. Whichever, sorry, which those I will replace, right? Whichever blocks will not be used in a while, those I will replace from the cache memory, because I am able to predict the future. That, like, let's say I know that before calling the one, okay, let's understand this. So here, right, I have called my 5, 9, 13, 7, all these are in cache memory, and then again I called 5 twice. Now as soon as I call 1, so there is a problem of replacement. So if I am able to predict the future, that in the future, let's say I had called 5, 9, 13 and 17 and then again 1. So I did not, okay, this is wrong, uh, 5, 9, 13 and 5 again. So in, like, this is the future, right? These are the future calls that the CPU will call. Okay, so I have to predict, I have to see that in future which one is not getting used. So I see 17 is actually not getting called in the future, so I will replace 17. But is that practically possible? This is not practically possible, right? This is not practically possible. Why is this not practically possible? How can you predict the future? How do we know that which block will CPU call next? Okay, so this is practically not possible, and this we don't use. So practically, Not possible. Why? Because how do we know? How do we know CPU will call which block? Okay. Next is the LRU. LRU is actually what we use. This is the most important one, and for your placement and everything, this is the most important one. This will be the most used one. So LRU means the least recently used. Replace the block that has not been used for the longest period of time. This is the most practical and effective approach, but it is quite complex to implement. Okay. So here, let's see here. Here if I see that here I have, let's say before the one call I am calling 9, and then I'm calling 13, and then I'm calling 1. So if I see, if I call 1 here, I have to check in the previous calls which one was called the least in the CPU request. So 5 was called thrice, okay, 9 was called twice, 13 was called twice, but 17 only was called once. So 17 is the least recently used. 17 has not been called for the longest period of time. So we will replace 17 then. Okay, so this actually takes into the effect of the past calls, takes into the effect of the past calls. Okay, so this is what we implement, and I will explain as well. We will come to this LRU slowly. So in fixed mapping there is no like block replacement policy, like everything is fixed, right? So there is no block replacement policy. In set associative mapping there will be block replacement policy needed, and obviously in fully associative there also will be block replacement policy needed if uh, if all the blocks are full in single block. So if all the blocks are full in a single like that cache memory, then only it will be needed. Else why do we need the block replacement, right? We don't need the block replacement if all of it is not full in the cache memory. So in the fully associative, if all the blocks in the cache memory are required, then only blocks then only blocks then only block replacement policy is required. Then only block replacement policy is required. Okay, so yeah, these are the things. What is the miss rate? Basically there is very high probability of miss rate because there are no alternatives of blocks placing in the same block number, because there is no like only one block can be residing in the cache memory block number. It is moderate, it is the lowest because of course I have so many blocks in the same set number. That's why it has the lowest probability of miss rate. Complexity will be higher here. It will take more number of space. Why? We have understood this previously. I will not explain. Okay. So let's understand with a example actually what does least recently use. I just given you previously a overview of least recently use. Now we will actually understand what does LRU policy means. LRU policy is definitely dependent on past, but how it is actually used, that we will understand. So here let's assume a two-way set cache associative. So my cache memory has two-way set of two sets, 4 blocks. So it has two sets, 2 sets, 4 blocks. Okay, so it is set 0, set 1, and each set can have 2 blocks. So let's say these are the calls and it is using LRU policy, replacement policy. 2 I call, so initially there is nothing in the cache memory. If I am calling 2, so where will the 2 will be placed? 2 will be 2 mod 2, that is in 0. So it will be placed in the 0, set 0, right? It will be placed in set 0. So here I will have set 0 of block number is 2, right? Cache memory block number is 2. Then again when I call 10, what is 10 mod 2? It is 0 again. So again 10 will be like, it is a miss because it is not present in the cache memory, so both will be miss. So this also will be missed, 10 will be placed here. Now next I call 2 again. If I call 2 again it is a hit, right? Because 2 is in the set 0, and in the set 0 when I will match the tags, I will see 2 is already present, so it will be a hit. It will be hit. No replacement is required. So nothing is required, just simple cache read. Now next I will call 6. Now if I call 6, if I am calling 6, that means what? 2 mod 6 mod 2 is 0. And what, like, where should 6 reside? 6 should reside in the set 0. 6 should reside in the set 0. So it is residing in the set 0. So now what can I say? What can I say is that it is residing in set 0. Okay, so it is not present, right? I will compare the tags. There will be a comparator. I will compare the tags. It is not present in the set 0. So if it is not present in the set 0, then I have to replace. Which one will I replace? Which one was the oldest that I did not call? So least recently used. So recently what did I use? Recently I used 10. No, sorry, recently I used 2, right? So I will not, of course, replace 2. I will replace 10 because recently I had just called 2. So I will not replace 2. I will replace whichever one was the least recently used. Least recently used is the 10. So I will replace 10. So 10 will be replaced to what? 6. That is what is written over here. So it is a miss, and replace 10 with 6. Next again I call 10. So again if 10 is called, now what is the, it is again, it should be again in the set 0 only, and again I compare the tags, they are not matching, so of course I have, it is again a cache miss. So if it is cache miss, that means again I have to go into the main memory and bring the block 10. Which one will I replace now? Which one will I replace? Which one was called least? So which one is called least? So just now I called 6, so of course I will not replace 6 because just now I have called 6, right? So I will replace 2 because 2 was the least recently used. So I will replace 2 to my 10. Again I am calling 2. So now if I am calling 2, now which one will be replaced? If I am calling 2, now my 6 will be replaced because just now I have called 10. So you might feel like, sir, what is the advantage? Because anyways again I am replacing these things. What is the advantage? Advantage is there, you will not understand. This is like a very worst case scenario I am taking to explain you the concept, but advantage is there. Okay, so this will be 2, set index will be 0 only, this will be a miss again, and now I will replace 6 with replace 6 with 2. Okay, so that is how it works. So let's take few more questions to understand this even further. So consider a direct map cache. So this is just a normal replacement policy. This is not even LRE policy. Okay, numbered from 0 to 7. So cache memory block numbers are from 0 to 7. If the memory block requests are in the following order, which of the following memory blocks will not be in the cache at the end of the sequence? So let me number the cache blocks, right? So I will have 0, 1, 2, 3, 4, 5, 6, 6, 7. So first I call 3. If I am calling 3, initially everything is empty. So if I am calling 3, 3 mod 8 will be what? 3 only. So it will be in the 3 only. Okay. Then I am calling 5. So 5 mod 8 will be 5 only. So like this is the cache block. So 5 is here. 2 mod 8 also will be 2 only. Then 8 mod 8 will be 0. So here 8 will be placed. Then again I call 0. So if I call 0, so 8 will be replaced with 0. Okay. Next I call 63. So if I am calling 63, 63 mod 8 will be 7, correct? Is it 7? Yes, it is 7, I guess. 56, yeah, 7. So it will be 7. So 7 will be here. Next, what do I call? So 7 not, 63 will be here. Next, what do I call? Next I call 9. So 9 mod 8 will be 1. So here I will have 9. Then 16 mod 8 will be 0 only. So it will be 0 will be replaced with 16. Now 20 mod 8 will be 4. So 4, this will be 20. Now 17 mod 8 will be 1. So this will be replaced again with 17. Okay. 25 mod 8 will be 1 again. So this will be replaced with 25. 18 mod 8 will be 2. So this will be replaced with 18. And 30 mod 8 will be 6. Okay, this will be replaced with 6. Okay, not this, not this 8. This will be staying here. This will be 6. 30 mod 8 will be 6. 30 mod 8 is 6. So yeah, it will stay here. Now 24 mod 8 is 0. So this will be replaced with 24. 2 mod 8 is 2 only. So this will be replaced with 2 again. 63 mod 63 mod like 63 mod 8 is 7 only, and it is already present, so there is no problem. There is no cache miss. It is a cache hit. Okay. Then 5 mod 8 will be 5 only, so 5 is already present. It is a cache hit. 82 mod 8 is 2. I have to replace 82 here. 17 mod 8 is 1, so I have to replace 17 here. 24 mod 8 will be 0. 24 mod 8 will be 0, and it is already placed in the cache, so it will be in the cache only. What are they asking? Which of the following memory blocks will not be in the cache at the end of the sequence? So if I see 3, is 3 in the cache? Yes. Is 18 in the cache? No, 18 is not in the cache. Is 20 in the cache? Yes, 20 is in the cache memory. Is 30 in the cache memory? Yes, 30 is in the cache memory. 18 is not in the cache memory. So option B will be correct. So for direct map, you don't have to think. Just write down the block numbers, just write down the sequence, what is coming, and just replace. Simply replace. You don't have to think about how to replace, right? You don't have to think about how to replace. Now, what can be the interesting question? The interesting question here will be the number of hits or miss in this whole sequence of operation. What is the hit ratio? If they would have asked the hit ratio, that is number of hits, number of hits divided by total whatever number of hits divided by the total total number of CPU requests. Total number okay. So hit ratio will be 3 by like I will tell you the answer, you will try to figure it out. I just telling you like hit ratio here will be like number of hits will be 3, because I had 3 hits, 1 hit here, 1 hit here, 1 hit here. That's why I had 3 hits. And how many requests I had? Total 20, I guess. 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20. So it is total 20, 3 by 20. So hit ratio is actually bad, but as we will increase our request, hit ratio will improve. So this will be into 5 into 5, 0.15. 0.15 will be the hit ratio. Okay. So from here you can actually find out the number of misses, number of like what is the average memory access time. All those things can also be asked in this question. So now let's understand the LRU policy with a question. So this is a GATE 2009 question. So here it is a 4-way set associativity, set associative cache, initially empty, with total 16 cache blocks. So I have total of 16 cache block. It is a 4-way set. So how many sets I have? 4, right? Because 4 into number of sets, 4 into number of sets will give me total cache blocks. So I will have 4 sets, right? So what you do is you just put brackets, okay, curly brackets, and the best thing will be to, yeah, curly brackets you put, and like you keep on writing the sets, okay. So I'll have 4 sets. So initially these are my 4 sets. So if I am calling for block 0, if I am calling for block 0, then like where will I place it? It is 0 mod set number, right? 0 mod 4, so it will be 0 in the set number 0, set number 1, set number 2, set number 3. It will be placed in the set number 0 only, so 0 will be placed here, okay. Then I am calling for block 255. So 255 mod 4, what is 255 mod 4? So if I remember, if I remember something correctly, that 255 mod 4 will be how much? So it is 240 into 80, not 80, sorry, 60, 60 into 63, 63 into 4 is 63 into 4 is 252. So it will be 3. Yeah, it will be placed in the set 3, okay. So 0 will be here, then this will be placed in the set 3. So 255 will be placed in the set 3, okay, because 256 is in the set whatever set it is in, okay. Next I have 1, so 1 mod 4 will be 1 only. Then I have 4 mod 4 will be 0 only, so 4 will be placed here. Then I have 3 mod 4 will be 3 only, so it will be placed here. 8 mod 4 will be 0 only, so it will be placed here. 133 mod 4 I guess will be yeah, I guess it will be 1, so it will be 133 will be placed here, okay. Next is 159 mod 4 will be 3, so it will be 159 will be here in the set number 3. 216 mod 4 will be 0, so 216 will be placed here. 129 mod 4 will be 1 again, so 129 will be placed here. 63 mod 4 will be 3, so 63 will be placed here. 8 mod will be 0. I have a cache hit, right? It is a cache hit, it is already present in the cache memory. 48 mod 4 is 0. Now 48 mod 4 is 0, okay. So but 0 is already full, so I have to replace something. Which one will I replace? The least recently used. Which one out of this, which one is the least recently called? So I am here in the 48. If I am here in the 48, now just check which one is the least recently called. So 8 was recently called, 4 was called here, and 0 was called here at the starting. So 0 was called the earliest, so I will replace it because it is the least recently used, okay. So not 0, yeah, it is the least recently used, right? Because 0 was called the earliest, that's why it will be the least recently used. So here 0 will be replaced with 48. Next I am calling 32. So again 32 mod 4 is again 0. So now which one is the least recently called? So 48 is recently called, 8 is recently called, my 4 is the least recently called now, because 200 was okay. Where is 216? 216 is here. So 4 is the least recently called, so I will replace my 4 with 32. Next is 73. 73 mod 4 will be 1, so 73 will be here. 92 mod 4, 92 mod 4 will be again 0. So again now which one is the least recently called? So my 216 is called here, 8 4 48 is called here, right? So 8 48, okay, 32 is also called, sorry. So 32 48 8, all of them are called, so of course I have to replace 216. So 216 will be the least recently called, so again I have to replace 216 with 92. 155 will be what? 155 will be mod 3, so 155 I guess is okay. 155 is not present, so out of here which one is the least recently called, least recently used? So 155 is I guess, yeah, it is 155. No, 155 is yeah, mod 3 only. Yes, 155 is mod 3 only. So here, right, which one shall be the least recently called? So least recently called out of this, right? So if I check here, 63 was the last one. After that 159, before that 3 and 255. So 255 will be replaced with my 155. Okay, so these will be the final updated blocks in the memory. Okay, so now if I see what are they asking, which one of the following memory block will not be in the cache if LRO replacement is utilized. 3 is 3 in the cache, 3 is in the cache. Is 8 in the cache, 8 is in the cache. 129 is in the cache. 216, no, 216 I just replaced, right? So 216 will not be in the cache if I use LRO policy. So one thing I just wanted to say, that you might have a doubt that what is the difference between the FIFO and LRE. FIFO is whichever one has came first, that one I will replace. It does not matter whether I am calling it again or not. So let's say first came 3, then came 2, then came 4. Then I call 3 again. Okay, let me give you an example. So first came 3, then came 2, then came 4, then I call 3 again, and then again. Now let's say it is a, then again I call, okay, sorry, not like this. So in this example only, so in this example, if I say, what if I would have used FIFO? In this example, what if I would have used FIFO? So if I would have used FIFO, so here when there was a debate, right, here there was a debate that, okay, 8 is already in the cache memory. For 48, which one will I choose? So when 48, I had 0, 4, 8 and 216. So if I had 0, 4, 8 and 216, right, which one shall I choose? I don't have to think about anything. Just go into the first one, whichever was entered first. So 0 was entered first, so I will replace 0. So in this case, luckily 0 was not called again. That's why both the FIFO and LRU are giving the same answer. Okay, whenever there will be repeated calls of the same cache block number, then FIFO and LRU will give different answers. Because if let's say if I here, right, in between, let's say 0, I call it again. So if I in between call 0 again, so 0 has been called. So now 0 will not be the least recently used anymore. Now what will be the least recently used? The least recently used will be the 4. Correct? Out of all these combinations, the least recently used will be the 4, because 4 is the block number which has not been called for a while. 0 has been called, 216 has been called, 8 has been called, right? So 4 will be the least recently used. But if I would have used the FIFO, then I would have replaced 0, because 0 actually was brought into the cache memory first. Okay, so I hope that difference you got between the LRU and FIFO. And LRU everyone will ask, no one will ask you the FIFO one. Okay, so that was the solution of this particular question. So now let's solve the next question. So next question is this one, where we have to consider a fully associative cache with 8 cache blocks numbered 0 to 7 and the following sequence of the memory block request: 4, 3, 25, 8, 19, 6, 25, 8, 16, 35, 45, 22. Okay, these are, if LRE policy is used, which cache block will have memory block 7? Okay, if LRE policy is used, which cache block will have memory block 7? So a fully associative, okay. So it's a fully associative cache block. Okay, it's a fully associative cache block with 8 cache blocks. So what will happen is, I will have 8 cache blocks. So this will be 1, 2, 3, 1, 2, 3, 4, 5, 6, 7 and then 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I have 8 total space. So what I will do is I will bring everything, right? So first 4 I will bring, initially cache is empty, so first I will bring 4, then I will bring 3, then I will bring 25. Okay, not like this, right? Where will each be stored? It will be like which one ever is the least recently used, like which cache block. Okay, so what are the cache block numbers? So this is the cache block number 0, 1, 2, 3, 4, 5, 6, 7, right? So it does not matter in which cache block number I will store. It does not matter, right? It does not matter in which cache block number I will store. Okay, so initially everything is empty. So everything will be put into the cache memory. Everything will be put into the cache memory. So initially 4 is there, then 3, 25, 8, 19, everything is a miss, right? Now everything is a miss. Okay, then I have 6, 25, again I call 8. So if I am calling 8, right, okay, I am calling 25 again. So if I am calling 25 again, so it is a hit. If I am calling 8 again, it is a hit. Okay, if I am calling 16, it will be a miss, so 16 will be here, then 35. Okay, so this is the first initial calls. Okay, initial calls. After this 45 comes. So now if I am calling for 45, which one will I replace? Which one will I replace? So if I am calling 45, so which one will I replace? I will basically replace whichever one was the call called the least recently used. So I see that 4 was the least recently used, right? 4 was least recently used, because in this case 4 was never called in between, right? So 4 was the least recently used. So I will replace 4 with my 40 with my 45. Then I will call block number 22. Now if I call block number 22, now which one will I replace? Now 3, right? 3 is the least recently used. 3 is the least recently used. So I will replace 3 now. Okay, so 22 will replace 3. Okay, next what will I replace? Next 8 is there, so 8 is already there, so I have already called 8 again, so 8 is already in the cache memory, so it will be cache hit. Next I am calling 3. 3 is again not in the cache memory. Now what is the least recently used? The least recently used is actually 19. The least recently used is actually 19, because in between, if you see, in between this least recently used, this last whichever one I replaced, and now whichever one I am calling, that is 3. If you see that here, right, in between the 25 was actually called, 8 was actually called earlier, 19 actually was never called here, 19 was actually never called here. So 19 will be the least recently used, because it was never called afterwards. It is it is only called once. So that's why 19 will be replaced with the 3. After 3, 16 is there. So 16 is already in the cache memory, so it will be a hit. 25 is there. 25 is already in the cache memory, so it will be hit. Then I call 7. So 7 is not in the cache memory. So where will 7 be placed? So now what is the least recently used? So 7 is here, and which one was the least recently used previously? The least recently used was 19. So in between 7 and 19, if I see, in between 7 and 19, if I see that 6, is 6 getting called? No, 6 is not actually getting called anywhere else, right? 6 is not getting called anywhere else. That means 6 will be the least recently used. Afterwards, if 6 was getting called, then I would have had to check 25 as well. So I'll just put a marker down here. Okay, that after this, after 19, only 6 was the one that was least recently used. So here 6 will be replaced with 7. So basically the value will be, finally it will be 7, right? It will be 7. Finally it will be 7. Okay, finally my, where am I storing the 7 value? In block 5. So answer will be in block 5, the main memory block 7 will be stored. 7 will be stored. So answer to this question will be 5. Option B will be the correct answer of this question. Okay, so these were some kind of example problems that can come. So now let's understand the concept of cache miss penalty. So what is cache miss penalty? So if I just show you what is cache miss penalty, we can check what is cache miss penalty. So the time required to bring a missed block from the main memory to the cache is actually miss penalty, right? So whatever the time I will require to bring the missed block from the main memory to the cache memory will be the miss penalty. Okay, this we have already discussed previously as well. Now we will go more deeper into it, because we have more knowledge about cache memory. Okay, so time to send the memory address to the main memory, time, so it is the time to send the memory address to the main memory. So then it is the time to access the required memory cell. Then it is the time required to transfer the data from the main memory to the cache memory. So let's take one example. So CPU will consume some cycles, right? CPU will consume some cycles, and also remember here the overall main memory access, right? because cache memory transfer happens in block, so I have to multiply the block size into the time required to access a single byte of data. So my main memory access time, main memory main memory access time will be the block size. Sorry for laughing, I'm just like thinking about event. Will be the block size, will be the block size into the time required to access a single byte. Time required to access a single byte in memory. Okay, so uh, so example is, let's say it takes us one CPU cycle to send the address to the memory. It takes us one 6 cycles to access one main memory cell. If the block size has 4 main memory cells, it will take me 6 into 4 cycles. Okay, and cycle transfer time to transfer one cell of data is 1 cycle. Okay, now let's understand this with an example. So let's assume that I have, let's assume that I have like my cache memory block size is 8 bytes. Okay, cache memory block size is 8 bytes. If my cache memory block size is 8 bytes and one cell main memory, this is my cache memory block size, and this is my main memory block size. Okay, so I have a cache memory block size and main memory, not main memory, cell size. So let's assume that a single cell of main memory is 1 bytes. So how much time will it take to do the data transfer? To send the address of the main memory, it will only consume me 1 cycle. So that is fine, 1 cycle. Plus to send, to access the main memory cell, one main memory cell, it takes me 6 cycle. So to access one main memory cell, it takes me 6 cycle. But actually how many main memory cells I need to access? Because I want to do transfers in block, right? So I have to actually access 8 main memory cells, because each cell is of 1 byte and I have to transfer whole 8 bytes. So I have to actually access 8 main memory cells. To access one main memory cell, it only takes me 6 cycles. To access 8 main memory cells, it will take me 8 cycles. So to transfer one cell of data to cache, it will consume 1 cycle. To transfer one cell of data to cache, it will consume 1 cycle. Okay, so if I want to transfer one cell of data from memory to cache, it will consume 1 cycle. But actually how many cells I need to transfer? I actually need to transfer 8 cells of data, because each cell is 1 bytes and I have to transfer total of 8 bytes. So it will be 1 into 8. So total it will be 48 plus 1 plus 8. So it is 57 cycles. So total it will consume 57 cycles. Okay. So total it will consume 57 cycles. Now let's understand a bit about the other one. Let's assume one more example. Let's assume my main memory cell size is 2 bytes. Okay, the cache memory block size is 8 bytes only, but the main memory cell size has changed to 2 bytes. Okay, main memory cell size has changed to 2 bytes. So now what will be the data transfer basically? So now if I see that to send the address to the memory, how many cycles it will take me? I just need to send one address, because that will be the starting address. After that it will follow sequentially. So to send one address, it will only take me, only consume one cycle, so it will be one cycle again. So this is total cycles, total memory cycles. Here also total. This will be 1 plus. Now tell me, how many cells do I need to transfer? Each cell is now 2 bytes. Okay, and I need 8 bytes of data. Each block size is 8 bytes. So how many cells do I need to transfer? 4 cells. How many cells do I need to transfer? 4 cells. And how many cycles it takes to transfer one memory cell? One cycle. Sorry, it takes 6 cycles to transfer one main memory cell from the main memory to the cache memory. It takes me 6 cycles, but I actually need to transfer 4 cycles. Sorry, I need to transfer 4 cells, right? Because each cell have 2 bytes, and total I need to transfer 8 bytes. So 4 into 2 is 8. So I need to transfer 4 cells, and each cell transfer time is 6 cycles. So overall it will take me 4 into 6 cycles. Okay, plus now if I have, let's say if I have like, now how much time it will take me to, like this was only for the access. Now how much time will it take me to transfer? So to transfer one cell, it takes me one cycle. I have to transfer 4 cells, so it will take me 4 cycles. 4 into 1. So total this will be 24 plus 4, 28 plus 1, that is 29. 29 cycles. Okay, so total it will be 29 cycles. Another example, if you want to take, right? Another example, let's assume that each main memory cell size is 4 bytes. So if each main memory cell cycle is 4 bytes and my cache memory is 8 bytes, so how many cells do I need to transfer? 2 cells. So now calculation is simple. Again, one cycle for the address, sending of address, then 2 cells into 6. Why? Because each main memory cell access takes 6 cycles. I need to access 2 cells, so it will be 2 times 6 plus the 2 into 1, because to transfer one cell of main memory it takes me one cycle. To transfer 2 cells of main memory it will take me 2 cycles. So this will be 12 plus 2, 14 plus 1, 15. So it will be 15 cycles. It will be 15 cycles. Okay, so yeah, that is how you find out. And what is the total time? So if some t clock is given, right, t clock will be given. So total time for this whole total transfer time will be the number of cycles into t clock. If t clock is given, you will just simply multiply the t clock and you will get the total transfer time. That will be the, this will be what? This will be the total transfer time or total penalty time. Why penalty time? Why penalty time? Because you had a miss. That's why you went to the cache memory. Otherwise, why will you go to the cache memory? So you had a miss. So you went. Sorry, you had a miss. That's why you went to the main memory. Otherwise, why will you go to the main memory? There is no reason of going to the main memory, right? So you had a miss. That's why you went to the main memory. So that is the reason why it is penalty time. Okay, because you have to go to the main memory and bring those blocks into the cache memory. That is the extra time consumed, right? So that is why it is known as the penalty time. So yeah, we have, like, this is whatever I have explained here, that is written in proper good handwriting, so for you to understand. Okay, so now everything was correct. Yeah, now let's solve few questions. So this one is the first question. A certain processor deploys a single level cache. Don't worry about this single level cache. We will understand multi-level cache in next lectures. The cache block size is 8 words and the word size is 4 bytes. So main memory, each cell of main memory cell size is 4 bytes because the data transfer happens in words. So cell size is 4 bytes and my cache block size is my 8 bytes. Okay, so this is the cache block size. Now what are they asking? Now it is telling me the memory system uses a 60 megahertz clock. So what will be the T clock? They have given me the F clock. T clock will be 1 by F clock. So it will be 1 by 60 into 10 raised to power 6. Okay. So next is basically this is the T clock. Now to service a cache miss, the memory controller first takes one cycle to accept the starting address. So one cycle it will take to accept the starting address. This is not dependent on the cell size. So one cycle anyways it will take to accept the starting address. Plus, now what are they asking? They are telling that it then takes 3 cycles to fetch all the 8 words of the block. Okay, it takes total of 3 cycles to fetch all the 8 words. So all the 8 words, because we transfer in, okay, we transfer in words, right? Each block, all the 8 words of the block. Okay, so to transfer all the 8 words, okay, the sorry, the cache block size is not actually in bytes, it is in 8 words. I'm sorry, that is what I was making a mistake. So it is 8 words, right? So to transfer all the 8 words, it takes 3 cycles. So they have already provided me that to transfer whole 8 words, it is taking me 3 cycles. So I will not multiply anything. So it will take me 3 cycles to transfer the whole 8 words to fetch all the 8 words, basically to access all the 8 words. Okay, then and finally transmits the words of the requested block at the rate of 1 word per cycle. So per cycle it takes me, I can transfer 1 word. How many cycles will it take me to transfer 8 words? Because cache block size is 8 words long. So for 1 word it is taking me 1 cycle. To transfer 8 words it will take me 8 cycles. So it will be 1 plus 3 plus 8. So it will be equals to 12 cycles. So now what they are asking, the maximum bandwidth for the memory system when the program is running, when the program running on the processor issues a series of read operations. Okay, what is the maximum bandwidth? Basically they are telling me at what speed I can operate, how much fast is my this memory system, right? So in it is taking me 12 cycles to transfer how many bytes? I am transferring a block of data, right, from the main memory to the cache memory. So a block has 4 words, sorry, 8 words, and each word is 4 bytes. They have told me that word size is 4 bytes. Okay, so if word size is 4 bytes, that means I am transferring 32 bytes of data. That is block size into 8. So it will be 32 bytes of data. Okay, it is 32 bytes of data. So block size is 4 into 8. Okay, so yeah, so now I am transferring 32 bytes of data. Now 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 what we can do is we can uh, change few things. So I consume 12 cycles to transfer 32 bytes of data. So to what will be the bandwidth? Bandwidth will be number of bytes divided by the time consumed to send those bytes, right? That will be the bandwidth time. So one cycle is how much? One cycle is T clock. 12 cycles will be 12 into T clock. So this will be number of bytes, that is 32 divided by, because they have asked, just see the units. Units is byte per second. So that's why it is bytes per second. So this will be 32 divided by the time. So time is 12 cycles into T clock. So 32 divided by 12 into T clock is how much? T clock is 1 by 60 into 10 raised to power 6. So this will be 5. So this will be 32 into 5, so this will be 160 into 10 raised to power 6 bytes per second. Bytes per second. So answer will be 160. 160 will be your answer. Okay, because basically they have asked the bandwidth, the rate at which data is transferring. That is what they have asked. The rate at which I can transfer the data. Okay. So that was for this question. So now let's understand another topic known as cache miss. So there are many types of cache miss. And why do I need to define the cache miss? You will say, sir, it is a miss, right? So simply I have to go to the main memory and bring it back. Then what is the requirement of knowing what type of cache miss it is? It is important because it will help me design the cache memory, which one I want the least. So like remember this, why do we need to understand different type of miss? Because I want to know the reason why that particular miss is occurring so that I can solve it. So types of cache miss tells me why that cache miss is happening, that particular cache miss has happened. So why that particular cache miss has happened. Okay, why that particular cache miss has happened, that you need to understand. If you understand why it has happened, then only you will be able to know how to solve it. If you know the reason why that particular cache miss has happened, basically you understand the reason. If you understand the reason, then you will understand how to solve it. Okay, so there are many types of cache miss. First one that we will learn is the core or compulsory miss. By the name compulsory, I hope you understand that it is something compulsory that I cannot avoid. I cannot avoid these kind of miss. Okay, it is compulsory. This happens only during the first access of a memory block. Let's say I want to access the memory register 3. The CPU request for the memory register 3. Okay, and of course initially the cache is empty and these are all blocks. Okay, these are all blocks, and initially let's assume my block size is 1 bytes. So my block size is 1 bytes. So if it is 1 bytes, initially I had a miss. So if I call 3, then 3 will be present over here, correct? It will be a cache miss, right? It will be simply a cache miss, and then again the 3 I will copy into the location block number 3. Okay, very simple. Now let's increase the block size. So it is a cold class cache miss because initially I don't have anything and it was a miss, so I have to go to the main memory and bring it. So this was a compulsory miss. I cannot avoid this kind of miss. If I increase the block size, let's increase the block size to 2 bytes. Okay, and let's first call CPU. Let's assume the CPU calls register 2. If CPU calls register 2, then it is a miss. That is fine, it is a miss. Then next what I will call, it is a miss, right? So of course it is a cache miss. It is a compulsory miss because initially it was empty. So I'll copy the whole block to the cache memory, correct? So basically the registers value 0, 1 will be stored in the block 0. The registers value 2, 3 will be stored in the block. This will be stored in block 0. This will be stored in block 1. Okay, and registers 4, 5 will be stored in block 2. Registers 6, 7 will be stored in block 3. Okay, so these are the registers basically. So like it will go on, right? Now CPU has called for 2 and it was a cache miss. Now next time if CPU calls for 3, if CPU requires the register 3, it is already present in the block number 1. 3 is already present in the block number 1 because previously I copied the whole block. So I copied 2 and 3. Now you might say, what is the difference, sir? So initially I had taken the wrong example. So initially let's assume if my block size is 1 bytes. Now if I call initially 2, it will be a compulsory miss. That is correct. It will be a compulsory miss. So that will be, as block size is 2, so that will be placed in the block number 2. So as block size is 1 bytes, it will be placed in the block number 2. Each byte will be placed in each blocks. Now next time again, if I call 3, again there will be a compulsory miss because I don't have anything in the block number 3, because each block size is 1 bytes. So again it will be a compulsory miss. Again I have to call the blocks. Okay, so it will be 1 byte. Now if the block size was 2, if you notice, so for block size 1 byte, both times I was having cache miss. Now if block size is 2 bytes, if block size is 2 bytes, now how many times cache miss I am having? Now how many times cache miss I am having? So if block size is 2 bytes, initially for calling 2 there was a cache miss, so I had to copy the whole block in the block number 1. What? Register 2 and 3, because now the block size is 2 bytes. So that's why I had to copy the whole block 2 and 3. Now next time when the CPU request for register 3, actually it is not a miss because it is already present in the block number 1. So that's how, if I increase the block size, my probability of compulsory or cold miss reduces. So I hope now you understood the solution and the reason why it happens. So reason why it happens, because initially everything is empty. So in the first call, actually, instead of just copying 1 byte, I copied more data to the cache memory. So if I copied more data into the cache memory, so there is less chances of having a miss if the CPU requests some nearby data of the initial call. So that is the solution. Increase the block size to bring more data with each miss. With each miss, if I will bring more data, that means there is a less probability of missing anything. Okay, there is a less probability of missing anything. Okay, so yeah, that was about it. That was about the compulsory and cold miss. Remember, sequence is very important. So first, whenever something will happen, first you will check for the cold miss. Okay, this is the first one that you will check, the cold miss. Now let's understand another type of miss, that is known as capacity miss. So in capacity miss, let's take an example first. Let's assume that I have 2 blocks. Okay, and I'm calling this request. CPU is requesting these blocks. So I have 2 blocks here. Zero and 1. Okay, so I have 2 blocks. So CPU request for blocks 0, 1, 2. CPU request for block 0, 1, 2. So it will be like in block 0, initially it is a miss, so initially 0 will be stored here, block 1 will be stored here. Now next time when I call for block 2, block 2 will have to be come here, right? It has to be replaced here. But let's say if I increase my size, if my cache size has been increased to 3 blocks, so if I increase my cache size, so it will be 0, 1, 2. Okay, so if cache size has increased to 3 blocks, that means this will be what? This will be initially this will be 0 because it is a miss, then 1 will be called, then 2 will be called. So actually I don't have to, like, the main thing is I don't have to replace anything, right? So now next time if my CPU request for 0 and then again request for 1, 2, I don't have to replace anything. There will not be a cache miss here, but here there will be a cache miss. So let's do the event. So now 2 has replaced here, right? Next again I call 0. If I call 0, again 2 will be replaced with 0, correct? So there is a cache miss of 2 times, and 2 times there are replacement happening here, right? There is only once the initial time, that is a cold miss. Initially cold miss is happening, after that there is no cache miss, all of them are in block. Okay, so after this, right, 2, if I call 0, 0 will be still present here, it will be hit. After it, if I call 1, 1 will be still present here. After it, if I call 2, 2 will be still present here. But here 0 is initially there, then I called 1, 1 will be here, then I called 2. So I have to replace 0 with 2, then again I called 0, then again I have to replace 2 with 0, then again I called 1. So again 1 is a hit, that is fine, but again if I call 2, again I have to replace 0 with 2. So there are so many misses. So this is known as the capacity miss. If my cache capacity is not enough, of course I cannot accommodate enough blocks. Okay, so how do you check? First you check for cold miss, whether it is a cold miss or not. So first sequence is cold miss. If it is not a cold miss, then you go for the capacity miss. Then you go for the capacity miss. Okay, so next, the last is the conflict miss. If, like as the name suggests, if it is not like this, you will check only capacity miss. You will check only if it is not cold miss. If it is not cold miss, then only you will come to check for the capacity miss. Conflict miss, you will check if it is not cold miss and capacity miss. If it is not cold miss and capacity miss, then only you will check the conflict miss. So it occurs when two or more blocks map to the same set in set associative or direct map cache. Basically, if it is a direct map cache, and even though my blocks are empty, but I am just replacing my initial block, right? 80808, something like that. So blocks are empty here. I have my storage. I have required space. I have space. Space I have. Okay. I have space. But actually the problem is the mapping, right? It is not properly mapped. So the highest problem will be in the direct map. There will be so many conflicts. In two-way mapped, the conflicts will be reduced because in the same set I can have two blocks, correct? In four-way, it will reduce further. So we have to increase the cache associativity. So we have to increase it either two-way, from two-way we have to go to four-way, from four-way we have to go to eight-way. Okay, and it will go on like this. Okay, so ultimately if it is fully associated, then there is no problem with that. Okay, so yeah, that is the conflict miss. Okay, so your first sequence will be checking the cold miss. First sequence will be checking the cold miss, then you check the capacity miss, whether the cache memory is full or not, then you check the conflict miss, whether like there is space in the cache memory but there are conflicts of the same block. So let's solve a question to understand the different kind of miss in an even better manner. So I have a cache with 4 blocks as a two-way set associative, right? So 4 blocks are there as a two-way set associative cache. So that means how many total sets I have? Total number of sets will be 4 blocks divided, total number of blocks divided by the number of ways, that is 2. So I have 2 sets. Okay, and initially cache is empty. The system uses LRU replacement policy. The CPU generates the following sequences of main memory blocks. So these are the sequences of blocks that the CPU requests. Identify the type of cache miss that occurs in the following CPU request. So this is my cache memory, basically this is my cache memory, and these are the calls. Okay, these are the calls. So if I see, initially I am calling 0 and initially it is empty. So of course initially I have not called 0 before, so it will be a miss obviously, and it will be a cold miss. So sorry, this side, this should have only 2 sets, it should not have 4 sets, so it will have 2 sets. So initially it is empty, so 0 will be placed here. Okay, it is a cold miss, it is a miss, it is a cold miss. Next I call 4, so 4 also has never been called before, and again I have space on the cache memory, so 4 will be placed here. It will be also a miss, but it will be a cold miss. Next I am calling 0, again I am calling 0, it is a hit because 0 is already present in the cache memory. Now I am calling 8, now I am calling 8, so 8 should be placed where? 8 should be actually placed in the set number 0 because 8 mod 2 is 0, and they have told me that we are using LRU, least recently used replacement policy. So as we are using LRU, least recently used, so LRU we are using. So here I have to replace what? Which one did I call least? Previously I just called 0, so of course I have to replace 4. So 4 will be replaced here with 8, and this will be also a cold miss. Why this will be cold miss? Of course there is a miss because replacement is happening. Why it is a cold miss? It is a cold miss because I have not called 8 before. I have never called 8 before. Just now I have called 8, right? So that's why it is a cold miss. I have not called 8, block number 8 before, that's why. Now again I am calling 0. So 0 is hit because 0 is already present. So 0 is a hit. Okay, again I am calling 4. So again if I am calling 4, now what is the least recently used? 8 is the least recently used. Again I have to replace the 8 with 4, and the important fact is what kind of miss is this? Of course I am replacing, so there is some miss. this miss is the type of conflict miss. This is a conflict miss. Why is this a conflict miss? Why is this a conflict miss? Because the cache memory still has storage. Cache memory still has storage and it is not a cold miss. Why it is not a cold miss? Because 4 has been called before. So I will write here 4 has been called before, hence it cannot be cold, cannot be cold, and the cache memory still has space. Okay, so if cache memory still has space, that means it cannot be capacity miss as well, it has to be conflict miss. So this will be a conflict miss. Next I am calling 1. So 1 never has been called before, it will be a cold miss and 1 will be placed over here. Next I will call 3. So 3 also never has been called before and 3 will be placed here, where 3 also will be cold miss because it has never been called before, and 3 will be placed here. Correct? 3 mod 2 is 1 only. Next I am calling 1 again, so it is a hit. Correct? If I am calling 1, it is a hit again, so there is no problem, there is no miss. Again I am calling 5, so 5 will be placed where? 5 will be placed in the set number 1. And which one I will replace? So just before 5 I just called 1, so 3 is the least recently used, so 3 will be replaced with 5 and 5 will be a cold miss because I have never called 5 before, so it will be a cold miss. Now 1 is a hit, 1 is a hit again, right? 1 is already present, so 1 is a hit. Now I am calling 3. So what will be 3? 3 cannot be cold miss because I have called 3 previously. So called 3 previously. So cold miss is not possible. Is it a capacity miss? Yes. Why? Because my cache memory is full. My cache memory is totally full. There is no space left. Okay. So my cache memory is full. Okay, so that's why it will be a capacity miss, it will not be a conflict miss. Okay, so how many total cold miss I have? Total cold miss if I count this 1 2 3 4 5 and I guess that's it, right? No, sorry, 1 2 3 4 5, yeah, that's it, I guess that's it. So this 0 was called initially, 1 2 3, 0 was called initially, 0 1 2 3. Okay, I'm just checking which one. This is cold, this is cold, this is not cold. Okay, this is cold, this is cold, 5 is cold. So 0 4 8, there are total how many numbers? 0 4 8 1 3 5, 0 4 8, yeah, there are total 6 numbers, so there should be 6 cold miss. That is what I'm trying to check. So 1 2 3 4 5, so where is the other one? So okay, this is the cold miss, this is the cold miss, and this is also a cold miss. I forgot to write here, sorry, I forgot to write, this is also a cold miss, right? This 5 is also cold miss. So total 6 cold miss we'll have. So initial calls, right, those will be my number of cold miss. The other miss, there has been one conflict miss and there has been one capacity miss. So number of capacity miss is 1 and my conflict miss is 1. Okay, so these are my total number of miss. I hope you have understood this part. Okay, so what is the conclusion? Conclusion is, if it is a first miss, if it is a first time miss, right, first time miss of that same block, then it will be a cold miss, then it will be a cold miss. Otherwise it will be either capacity or conflict miss. So if, then after that I will write here summary. After that, if the cache memory is full. If it is not a cold miss, that it is not a first time miss, and if the cache memory is full, that means it will be a capacity miss. Cache memory is full, it will be a capacity miss. And if cache memory is not full, if cache memory is not full, it is a what? That means it is a conflict miss. So this is the main summary that you need to take away from the types of misses. Okay, it is not that misses, it is a type of miss. So like this is the summary also here. If the block is accessed for the first time, then it will be cold miss. Cache cannot hold any other working set, that means there is no space in the cache memory, so of course it will be a capacity miss, otherwise it will be a conflict miss. If the block maps to the same set, that's why it will be a conflict miss. Okay, so now let's solve this next question. So you can try this question out, and then of course I will solve this question. Okay, so we have a two-way set associative cache with 256 blocks. So total number of blocks is 256, and it is a two-way set. So how many sets will I have? How many sets? So number of sets, number of sets will be number of blocks divided by number of blocks divided by the way set divided by 2, right? So it will be 128 sets. There will be total of 128 sets. Okay, got it. And each set has 2 blocks in it, and we follow the LRU replacement. Initially the cache is empty. Okay, conflict misses are those misses which occur due to contention of multiple blocks for the same cache set. So they have also defined what is a conflict miss. Compulsory misses occur due to the first time access of the block. The following sequence of accesses to the memory blocks are given is repeated 10 times. Okay, this sequence of access is repeated 10 times. The number of conflict misses experienced by the cache will be put. So in the first set, we will just see in the first iteration how many conflict misses are there. Okay, so initially there is nothing. So where will 0 will be mapped? 0 mod 128 will be 0 only. So 0 will be mapped in 0. So initially it is a cold miss, because previously I have not called 0. So it will be a cold miss. Okay, so initially this will be a cold miss. Just we have to keep the track of conflict misses and compulsory misses. Also they have told cold miss or compulsory miss are same thing only. So initially, okay, so this is not cold, compulsory, like they are telling this is compulsory miss. Okay, they have just changed the name, both are the same thing only, compulsory okay. Next is the 128 is here. So 128 mod 128 will be 0 again. So if 128 mod 128 is 0, so of course in the set 0 I will change my okay, the number of sets repeated 10 times. So in the set 0 I had 128. Okay, I had 0. So as 128 also should be stored in the set 0 only, I have a space, right? It is a two-way set, so 128 will be stored here, and of course I am going to the main memory and taking some value back. So it is a compulsory miss because I had not previously called the set. Okay, then 256 is there, right? 256. So if 256 is there, again if I do 256 mod 128, again it is 0. If it is 0, now I don't have any space here, so I have to replace something. So I am following a LRU replacement policy. So if I am following LRU, which one was the called last? This 0 was called way back, right? Just before this I had just called 128, so I will not replace 128, I will replace 0. So 0 will be replaced with 256, and again it is a compulsory miss because previously I had not called this, so this will be a compulsory miss. Now I am calling 128, it is a hit because 128 is already present in the cache memory. Now again I am calling 0, so 0 now is a conflict miss. Why? Because cache memory is free, right? I have still 127 sets free, cache memory is free, but this 0 is not in the set 0 because it is supposed to be in the set 0. I had just replaced the set 0, right, this block, and this is not a compulsory miss because 0 has been called previously, so this will be a conflict. Now 128 is, so again I will replace, like which one will I replace? I will replace 128, just like I want to write 0, right? I want to get the 0. Which one will I replace to write 0? I will replace 128. Why will I replace 128? I will replace 128 because previously I had like previously I just called 256. I will not replace 256 before 0. Okay, no, before 0 I just called 128. Sorry, before 0 I just called 128, so I will not replace 128, I will replace 256 because 256 was called earlier, so I will replace 256 to 0 again. Now again I am calling 128, it will be again a hit, it will be again a hit. Okay, this will be again a hit. Now again I am calling 256, again this will be a conflict, again this will be a conflict. Why this will be a conflict? This will be a conflict because 256 is not present in the set 0 and 256 has been called earlier, so it will be conflict. Now which one will I replace? So just before this 256 I had just called 128, so 128 I will not replace, I will replace 0 again because 0 was called earlier, so 0 I will replace again with 256. Okay, 0 I will replace again with 256. Okay, now again 128 I am calling, 128 will be again a hit, 128 will be again a hit. Okay, this will be again a hit. So until now only two conflicts I have. Now I am calling 1, so 1 will be placed where? 1 will be placed in the set 1. Okay, 1 will be placed in the set 1. In set 1 I will have 1, so that is only 1. Okay, next I have 129, so where will I place 129? 29, again 129 will be placed in set 1 only because 129 mod 128 is 1. Okay, now 256 mod 128 is also 1 only. So again in set 1 I have a code miss because this will be code miss. Why? So all these were code misses because these were all the initial calls, so these are all compulsory miss. This 129 is also compulsory miss, this 257 is also compulsory miss. This is not a conflict miss because I have not called this before. Now which one will I replace here? So out of these two I will replace 1 because just I had called 129, so I want to place 257, I have to replace 1, that is the least recently used, so I will replace 1 here with 257. Okay, with 257. So next is 129. So yeah, 129 29 is already here, so it will be a cache hit, and again I'm calling 1. So if I'm calling 1 again I have to replace something, right? So before calling 1 just I had called 129, so I'll not replace 129, I have to replace 257, so I'll replace 257 with 1 again. Okay, I will replace 257 with 1, so 257 will be replaced with 1, so again this will be a compulsory miss. Now this 1 will be a compulsory miss. Why? Because 1 was actually previously called, so this 1 will be a compulsory miss. Okay, this one will be a conflict miss. Okay, this one will be a conflict miss. Okay, this one will be a conflict miss. Now what about the 129? This 129 is already present in the cache memory, so this will be a hit, this will be a hit. This 257 is again not present, and again which one I will replace? I will replace 1 here because 129 was just called, so this will be again replaced with 259 257, and again this will be a conflict. Okay, so how many conflict I have? So if I see, I have here, from here I have one conflict, two conflict. I have two conflict. Now again I am calling 129, so again it is repeated, so it will be again hit. It will be again hit. So this was for the first iteration. So first iteration has total of two conflicts here plus two conflicts in the set. So this is for the set 1, sorry, set 0, and this is for the set 1. Okay. Now actually, right, after this I will not have any compulsory miss, because like they are telling me I am repeating this calls 10 times. So if I am repeating this call 10 times, initially there was nothing in the cache memory, that's why all these were compulsory miss. But as soon as I will repeat this again, so again 0 will be called here. Now 0 will be called here, and if I see on the set 0, that 0 is actually not present. 256 is present. Currently 256 is present in the set 0. So if I call 0, it will be a miss, and it will be a conflict miss. It will be a miss, and it will be a conflict miss. Okay. So currently, what is the current status? So my set 0 has what? My set 0 currently, my set 0 has 256 and 128. My set 0 has 256 and 128. Okay. And my set 1 has what? Currently my set 1 has 257 and 129. 257 and 129. Now again I am repeating this sequence. Okay. Again I am repeating this sequence. Now nothing will be compulsory miss, because these all have been called previously. So I am in the loop I equals to 1, that is in the second iteration. So this was the first iteration. So due to the first iteration, everything was empty. So this is the first iteration. Okay. Now we will discuss about the second iteration. So in the second iteration, initially, now if I am calling 0, 0 is not present in the set 0, right? Which one will I replace? So which one is the least recently called? So if I see from here, recently before this one, right, 128 was called. So 128 I will not replace, I will replace 256. So 256 will be replaced here with 0, because this was the least recently called, and it is a miss, it is a conflict miss. It will not be a compulsory miss, because it is not like I had called 0 previously. This is the first iteration, right? Sorry, this is the second iteration. Now again I am calling 128, 128 will be hit again here. Again I will call 256, again 256 will be replaced here. So again there will be a conflict miss here. Conflict. Again I am calling 128, it will be hit again. Okay. Again I am calling 0, again it will be, this one will be replaced. So this will be again a conflict miss. Again I am calling 128, it will again be a hit. Again I am calling 256, it will be again a conflict miss. Okay. It will be again a conflict miss. So total in this whole range for the set 0, I have 4 conflicts. And now let's check in the set 1. This is for the set 1, right? In the set 1, I am calling 1. Okay, this is this should be 129. Yeah, this is 129. So I am calling 1, and 1 is not present in the set 1. It should be present, right? So which one is the least recently used? So 129 I had just called. 129 I had just called. So 257 will be replaced here. So 257 will be replaced to 1, and my 1 will be the conflict miss. Okay. Again I am calling to 129, which is already present, so it will be a hit. Again I am calling 257, this will be changed to 257, and this will be again a conflict miss. Again I am calling 129, again it will be a hit. Again I am calling 1, so 1 will be again 257 will be again replaced. It will be again a conflict miss. Again I am calling a 129, so 129 will be again a hit. Again I am calling 257, so 257 will be again a conflict, right? Because 1 is there currently, I will replace 1 with 257, so again it will be a conflict. So how many conflicts I have? 1 2 3 4. So here also I have 4 conflicts in set. This is for the set 0 and this is for the set 1. So this will repeat actually. After the second iteration, it will just repeat. Okay. For how many times? So one iteration I have already done. So I have 9 iterations left. So in the first iteration, so total conflict misses, because they have asked in the question, if you see in the question, they have asked the number of conflict misses experienced by the cache. So the total number of conflict misses will be, it will be equals to 4 for the initial iteration, and then how many iterations I have left? 9. And in each iteration, how many conflict misses I am having? 4 for set 0, 4 for set 1. So it will be 4 plus 4. Okay, and this will be actually 2 plus 2. So this will be the set 0, this will be the set 1 initial. Okay, and this is for the set 0 and set 1 after it is like after the compulsory misses have been done. So it will be total 4 plus 9 into 8. 9 into 8 is 72. So it will be 76. So total 76 conflict misses I will get if I repeat these calls 10 times. Okay, so 76 will be the answer. This is a very, very good and elegant question. So I hope you have enjoyed this portion. We have done a lot of difficult question, and it's fine if you are not able to understand this the first time. You have to watch the video over and over again, then only you will be able to understand it. It is not an easy concept. So I hope you have enjoyed this lecture. If you did, make sure to hit the like button and subscribe, and comment down below if you are learning new things. Okay, so I will meet you in the next lecture. Until then, happy learning.